Cool. Well, we are waiting to see if anybody will come. Um, just quickly, any questions on latent music stuff? Have you watched the recording yet?
There's like the two different like control net and ditto.
Mm-hmm.
So are those usually used like alongside like some other like model? Like are they the only source of like the voice generation?
Yeah, these two assume you have that model already. So text to music out model. So in this case, this is the text to spectrogram model. And the idea is that even with this model, with some text, you still have the Z, right? And whatever Z will give you a slightly different version of this, upbeat James music. And any of this point in the Z space will map to a specific spectrogram, and they will have like different controls. So some of them will have that, desired dynamic of this, some of those will be this way, and any other shape. So basically the idea of ditto is just that, well, I just pick this knob and then move it around to see where is the point where you get that desired shape. So that's the idea of ditto. So you don't actually need to train anything. You're just trying to find out the best, latent Z that leads to the desired feature. And music control net is basically training a sort of like a pseudo pair here that will add something to this unit. So you are, so this is the original model, just some text, and then go to this pre-trained unit and get some background. And now you are adding these conditional thing, and you want to affect how you generate the music.
Like the control branch, it's like during the diffusion step.
Yeah, it's in each distribution step. So it will happen actually like thousands of times. So each diffusion step will be added with that control net. So this thing is just one diffusion step. And you do this 1,000 times. So in every diffusion step, you want to know how you use that control to affect the original one. So at the left is the original one, and at the right is the control net that you train. So everything at the left is not trained. Everything at the right is trained. So now you are basically affecting these decisions. So to think about it is just like, well, the model does know how to generate music, right? It just doesn't know where to gear that music towards. And now the control net is just like adding those information so that, and you see that, encoded everything. And now these control net is just adding to the output layer. Try to do some modification on top of it. Yeah.
Wait, it modifies like the weighting factors that you go.
These everything. It's just like adding on top of those outputs. So it's not, yeah. Yeah, so it's actually something like this. So you go from X and then you go to Y, right? That's every single block. What you want to do is that now we will add this something to this Y output. So it's like residual net. And the idea of control net is that this thing defaults to do nothing. So when you train this, originally everything past here is 0. So it won't affect the original thing. So, when you want to fine tune this control net, so you get a very good text to music generator. It just doesn't know how to follow your control. But, it's still better that you generate, some deer. It's just not in that specific shape. But at least you are generating some deer. That's when you get started. And now you just fine tune it to make it into the shape. Yeah. So that's the whole idea.
Yes. Slow control about how to music generation.
Yeah. So, yeah, technically it's not just fine tune, it's actually training a new set of, controls on top of what you have originally. Yeah. So calling it fine tune is a little bit tricky because it's not fine tuning the original one. It's sort of like training an adapter that just like attach on top of your original network. So you think about this as like something attached, like an alien attached to your model, and that will just like injects some influence into your output. Yeah. And this thing will understand how these conditional signal work. In this case, like, dynamics, core structure, anything that you can pass into this. And yeah. So you see that this also have the exact same shape of this thing. So this thing actually take the same shape of input. And that's essentially why control net is so influential, because this is the inputs, it's the same shape of your outputs. So you can do that very fine grained controls. And the same as here, like the inputs and outputs is the same shape. So basically you are doing to UNet shape is exactly the same shape, just that this one is smaller than this one. Yeah, in terms of the number of parameters he has, because it doesn't need to do a lot of things. What it does is to understand what your control is, try to influence the original, model. So it's not drastically changing stuff. It's more like gear the original model towards, because the model does know how to generate this, deer in this pose, just that it doesn't know why I should do that. Because if you just don't put the conditional input to it, if you just say something like, whatever prompt, it would just generate some random deer at a random pose. Yeah. So that's basically the two dominant ways of doing controls, and people are still looking into some other way, but these two are kind of dominant. One is training required, one is only inference time tuning. Yeah.
I guess I don't know if this is like a question that what would be like the thing used to train control net? Like, would you have like augmented examples or something like that?
Oh, you mean the music?
Yeah, how do you train like the control net?
You mean how to train it? Technically, you're just doing the same training, just that now you have the input. So the training is the same, right? Just that now you have additional. So what you want to do in the original diffusion is that you have some text and you have the output. When you are training this diffusion model, you know exactly what's the next step. You predict the noise, right? And you want to remove that noise. Now it's like given this particular condition and the prompt, and the output should be like this. That pair output. So now given this plus this prompt, you want to generate this image, and you do know how you can get all those noisy inputs. And the reason why in control net, we usually will aim for something smaller, because this data set is much trickier to get than a typical data set where it's just a bunch of image. So think about the human post one. It's like it's just human, like everything else you cannot do it like that. So the data set will be much, much smaller than the one that you train the stable diffusion for, the latent diffusion model for. So this latent diffusion model might be able to do both of these, and also, landscape or, room layout or whatever images, or even, cartoons, manga, whatever. But in this case, you are training the model to do a very specific job, and you only get fewer examples. Yeah, but the training is the same. Yeah, given this plus this, you want to, you know, learn to remove noise so that you get to the desired output. Yeah. Yeah, so technically it's the same. The big innovation here is how you try to initialize it to do nothing when you get started. Because the worst case you want to do is to just ruin everything you know about stable diffusion. Now you just want to inference it, gear it to what you want. And assuming that your model does know how to generate a person in a specific pose, just that it doesn't have that input and doesn't know how to interpret that input. But once you train this control net adapter, Now the model does know, well, this is the pose you want, and I do know how to generate that. Now, given that condition, how do I generate those? Cool. I mean, this is very ongoing, as you see. Both are 2024, and Dito has also second version, Dito 2. A lot of things going on recently. So, especially think about how this can be useful. Think about music generation might be a little bit tricky. It's like, in what case we want this, but if you think about, for video, for a specific, audiobook or whatever, where you do have some cues that you have to match, say, yeah, exactly. And also like climax or, plot scene change where you do want the scene change happen at the specific points and say this is your, main part of, narrative. That's the climax. And then you want to do it. So you can actually draw these curves. And Ditto is from UCSD plus Adobe. So soon we will see, Adobe Premiere Pro to have something like this, hopefully. Yeah. Um, but at the same time, you can also use this as like a DJ, I don't know. But also gaming. I think there's tons of application people haven't really looked into yet. Or, think about even like real time. Can you do this in real time? Say your hand gesture just mapped to certain features and you just real time trying to gear the things according to more semantical things. So what people have done is that, well, just you ditto and we basically just map our hands into this space. You can grab it and just move it around and you do get different sounds for the same prompt, but it's not, grounded by some semantical understanding. It's just like, well, we're just randomly walking around that space. But what if you can actually map it to a specific, say, say my right hand maps to dynamics, left hand maps to a certain, tension or whatever chord progression, and can you use that to control these kind of model? So ongoing and not sure where it's going yet. Cool, but basically we gone through this, latent music generation part, and this is actually how most recent music generation model are how it works. Kind of most of these models is based on this kind of architecture. The reason why is because this is much more efficient. So think about why should we generate waveform in any case? If you can do this, now you are generating in a much smaller space where these codes are tend to be, smaller. And, this decoder is just like, think about MP3 codec. You can always think about a much more efficient codec. And now the goal is to generate those codes with lower cost. There's also other benefit, but this is sort of mainly the reason. And latent diffusion model is sometimes called stable diffusion. Because think about what it does is that, well, whatever you do, whatever you generate here, it will later be decoded by your decoder. So think about this decoder, how it is trained is that, well, it learns to map anything into something real. So it does have that benefit of, even you generate something really bad here, it still will be decoded into something real. So that's the additional benefit of these stable diffusion or latent diffusion model where, because you have this decoder, they will learn to fix all the artifacts for you. So you don't really need to worry about what you get here. Of course, you want it to be better. Cool. We look at, audio gen, transformer-like language translation-ish from text, English to like an alien language. But you can think about those are like MP3 bytes or whatever. It's just some language that you don't understand. Musical lamp, a bit more complex, but the same idea, where the key idea is in this Mulan thing, where during training, you use the audio to extract those tokens, extract those conditional inputs, sort of audio embedding. And during the inference time, now you only have text. But given that Mulan understands text and audio and throw them into the same shared embedded space. Now you can actually just throw that text to that space. Now you can do the same thing as when you train it. You know how to go from Mulan to the semantic thing. This is the model you train. And here, given these two, you know how to do this because this is the model you train. And in the end, you will get your audio. So that's how a lot of nowadays models are doing, because this sort of like disentangle the idea of text and music understanding with these generated process. And part of the reason is because of the legal concern. So Mulan is trained potentially on more copyright data. The license works slightly different for when you want to train this understanding model, generative model, or the sound stream, the codec model. So it's always good to differentiate these components so that you can apply different license, get different data set to train each of these components. So nowadays, this become more engineering than needed, but it's getting commercialized. And this is the things behind Google Music FX, but also Music FX DJ is actually based on something similar to Music LM, but it's now can be run in sort of real time-ish. Latent diffusion model is the other thing we talk about, but I guess the key is that it's just a bunch of stuff added together. And it has the name diffusion because that's the hottest topic then, but it's inherently sort of everything combined. The only one we have, not the only one, I mean, the most famous one we have in academia is rare because the data set is much trickier to get from academia. So in industry, they usually just buy, stock music, license it and to train their model, or some company do it shady, like just don't do any buying. But in academia, it's much harder to get these data set. But anyway, Music LDM is sort of testing this idea. There's also other models that just do slightly different from, just text to music. So that is just like thinking about, well, can we crop out part of it and revamp it? And with this idea, the idea is similar to, like Coconut or Debug, how they do it on Piano Roll. Now you are doing it in this token space. So you learn to sort of like reconstruct these tokens, and these tokens correspond to these tokenizer and decodenizer, but those are basically neural codec as we talk about. And this can enable a lot of like interesting application where you can just periodically crop out stuff, beat-driven crop out. You can even do implanting. You can also mash up two songs by just taking, this one from A song, B song, A song, B song, A song, B song. You can do some mashup. Quite interesting. And this on loop thing is also cool, where you grab the same audio and then you just loop it while making slight difference variations over the time. And so this is like sort of like a live, looper, basically, that won't repeat itself. We talk about control net and Ditto. Cool. So we are pretty much done with the creation part, but still, I mean, creation doesn't just end with, the musical idea. There's a bunch of, music production going on. So, we haven't talked about, how we do it in DAW, how we do the mixing, how we do all the effects. And that's what we are going to talk about today. Cool. Cool. So, music production and editing. It's getting more popular and popular, intelligent music production. So, if you think about music production, it's, different from music creation, or, it's part of music creation. But, think about when people think about AI music generation, it's just like, oh, can we generate some, baccarels? Can we generate some classical music? Can we generate some certain sample? But on the other hand, in music industry, if you are in the industry, then, think about music production, people might think about this. You have DAW, you want to see how you compose music or how you can edit your music. And, it's even further than that. There is some hardware component that it's just not about just in DAW. So this, again, like an oversimplified music production flow. So, you go from composition, arrangement, and you go to a performance or recording. But, there is a tons of, music production going on even after the recording. How do you mix them? How do you edit it? And next lecture, we will also look into how you do recommendation, how you do retrieval, so that distribute music to different customers. But how do you publish it? How do you detect copyright? How do you do watermarking? So there's a bunch of stuff after even you have the first musical idea. How do you actually make it into the final music and then deliver it to your listeners? So one thing about Dole is that, well, this has exist for years. So, this mix assistant is actually started in 2019. So this is Isotope. Isotope is sort of like leading this intelligent music mixing or production tools. Um, I think it's now bought by the same company as NI. So I think recently three of them merged together into a bigger company. But anyway, Native Instrument, I think they are now in the same parent company. But anyway, Isotope some of these efforts. We can take a look on what this is. So this is in like 2019, and they usually code it mixing assistant.
Let's try Mix Assistant's results on a few more sessions in other genres.
This is actually not doing a lot of mixing. So this is mostly just doing leveling and panning. So, you have all these tracks. How do you group them together to have these leveling? Because, without mixing before this, you can hear that the level just different. And so you choose a focus track that will have a higher level than others. But you also want to balance them, and you want to pan it so that you create that sound stage with rather than everything stuck in the middle. Cool. I think the label they will also automatically do it. Yeah. But you have to choose the focus one. So even it classify into voice, bass, percussion, musical, you still have to choose one of those as focus. That will especially be useful when you have just instrumental. When you have vocal, well, likely you want to put local in the focus, but if it's just instrumental, then you want to see where are the focus. But it will get a little bit tricky because think about because we recently are doing some research on acapella, and acapella is like basically you change the focus every time, so that thing is just changing. But also in instrumental, especially like very lively, improvisation. But at the same time, you can just have them as focus. But the mixing part of it is just tricky. But anyway, this is just 2019, and after that, still lots of things going on. But at the same time, there's also this master system. So mastering is different from mixing, where mastering is thinking about, well, once you've done the mixing, now you think about, potentially your music will be listened on so many different devices. So now, we have this generic, very nice, monitor speakers, and you mix, in some studio that has very nice speakers. But people might listen it to your laptop speakers. People might listen it to your phone. Might listen it like I don't know, like airplane, those tiny earbuds, and in very noisy environment. So mastering and thinking about all these potential cases and want to see whether your mixing outputs can still work on all these extreme conditions. And you have to think about potentially on different platforms you want to master it into a different formats. So likely you also see in Moesis, there's this AI mastering thing. So you can give it a try. And so last semester, there's also a group of final project doing this to see AI mastering, and they found out that with the good, headphone that we have at Pat. And looking at some students, undergrad students, listen to AI Master ones and students Master one. It's very hard to find the difference, although it's technically the professional Master one. But that sort of give you an idea that these algorithms give you a very good start to base on. Cool. So, man, of course, mixing and mastering is not just about, just leveling and panning. There's a bunch of stuff going on. You want to add reverb, you want to use compression, you want to apply EQ to that. So every of these, we sort of use an umbrella term called audio effects. This is not to be confused about to sound effects. Because sound effects is, when you're doing sound design, you want to do Foley, you want to do explosion sounds, but audio effects, you can also be referred to those. But here we are talking about these kind of things. So, EQ, equalizer, compression, gating, reverb, delay, wet dry, blah, blah, blah. So, different things that you can do in DAW, basically. And these are just like a two-way of how these effects can be sort of like categorized. So insert FX basically means that you grab something and then you do something and then the outputs will be different. So, think about EQ, compression, and gating is that, the inputs and outputs, you want to replace the input entirely. But there is also send FX. So this is sort of like doing a copy on the site and you want to add it to the original one. So think about reverb. It's basically, I guess first think about delay. You want to delay it so that you create that echo effect. So you want to have this and then you want to delay it and then add it here so that you have these things and then delay for 100 millisecond or a second and then you add it back. And if you do it a lot of many times and do it with some decay, then you get the reverb basically. 100% wet is sort of another thing. So you have dry, wet, encompasses two different components. Like the dry is the original sounds, and the wet is like the process sounds. And how do you combine that? 100% wet meaning that you basically just want the process sounds. Cool. So I would just go over some of these, likely most of them, but just to remind you, there's like different audio effects. So EQ is likely the one that you might want to play the first time you get a DAW. So traditionally something look like this. So basically, 8-band EQs. Is this 8-band? More than 8 bands, 10 bands EQ. So basically these are the different frequency as you can see at the top, 31 Hertz. So these are bass, 63, 200, 500-ish. Then these are the lower octaves of piano, 1 to 4K. Then you enter in vocal range, 8K, 16K, likely very high frequency range, strings or, high octaves of piano or guitar. But anyway, and this is just a more modern version where you can do all sort of like the actual frequency response that you can do. So you can grab each of these peak. You can, boost this 2K where you have the vocal. You could also remove certain mode that's, potentially when you are recording the sounds, there could be certain, standing wave that emphasize a specific frequency. So you want to get rid of those. So, EQs are very useful in doing that. So equalizer. So you can think about equalizer as just a filter on top of the frequency response. That's an easy way to think about equalizer. Dynamic range compression. So maybe you know about loudness war. So basically nowadays, songs are getting louder and louder, and that's, grounded by some, study that, basically human will think louder music sounds better. And so the idea of dynamic range compression is that, so now we just want it to sound very loud all the time. So, think about classical music. If you've ever listened to classical music, on Spotify or any streaming platform, then you will notice the huge difference between classical music recording and pop music recording. That pop music recording basically all time loud. Classical music, you will have that very, very high contrast. So the contrast is here what we call dynamic range. So what's the maximum volume and what would be the say forte piano contrast. And in pop music, we just mostly nowadays it's getting smaller and smaller. So forte and piano doesn't have a real big difference in their loudness. This is achieved by something called compressor mostly. So compressor is the idea where, at the x-axis is the input level and y-axis is the output level. So basically the idea is that you lower those contrasts at the very low volume part so that you can bring everything up. This is a bit, counterintuitive, is that you are clipping a very loud volume down. But at the end, you want to also bring that to be the full volume. So you sort of like make all these very loud sounds originally, very loud input sounds, and you reduce its loudness by 50%. And then you bring these things back to this shape. So you will get something like going from here to here and then going down. So now everything sort of like become louder, but you lost the contrast at those louder regions. So this is called compressor. Basically, you want to determine what the stressor will be. So after this point, you want to do this, minus 50% loudness cut. You can also do it more. Then you can do minus 75%. That's called for 4-to-1 compressor. And you can even do it in stream. That is when we call limiter. Basically, you just clip it to a certain volume. So you can think about this, basically just break that contrast or dynamic range on louder portion of your music. Cool. So that's compressor, but also, think about leveling and panning. That's like we see in the mix assistant things in Isotope. Why do we care about leveling and panning? This is because, spatial placement of sounds. And when you want to do the music production, oftentimes you will have microphone on each of the instruments or, potentially certain places in the concert hall in this case. So, after that, then how do you place these sounds in your soundstage? Think about very different ensembles and every single ensemble, there could be, exactly where they are, but also at the same time, when you want to mix it, then there's like artistic decisions that you have to make to design your soundstage. So this is like the kind of official, semi-official reference guide from Pro Tools. So, listen here, and this is sort of like what you likely will hear for lots of the pop music nowadays. So usually one thing about, low frequency and high frequency works slightly different. So low frequency, usually you are not so sensitive where it's coming from. And that's why sometimes you see those bass actually doesn't has to be, in the middle when you have the speaker. But usually when you are mixing it, you will put the bass and drums in the center with the lower end and the lead vocal, of course, in front of you. But everything else, then you can sort of like pan it to create that soundstage. So you could say, lead guitar here, but, you will have background vocal at the sides and, kick drum in the center. That's the bass. But all the other, drum sets will be at different places. So this is sort of like a planning reference. So that's actually just translate to this visual mixer things that we saw. So this like balance assistant is basically once you click it, it will do some AI. And this is like in 2019. So this thing is 2017. And 2019 that add this, assistant thing. So it's really cool because, actually these AI tools already there. And, some of these model back in the stage already have this source separation, stem separation things, even before AI, you can do it with signal processing. And they usually call it assistant and then later intelligent. And now they will finally use sort of like AI-ish things. But sometimes it's just signal processing, but sometimes it could be AI models. But this is basically the same idea, at the top is a louder. So here 0 dB is where you just don't change its volume. If you lower, then it's quieter, and L and R left and right. So basically you put the lead vocal in the center, and you have the drums, of course, bass in the middle, because those are the, the lower frequency part. You want to keep it in the center. Otherwise, the volume will be different with L left and right channel. And now you can expand that, guitars. You could do all sort of like pairs of those. And this is like double track, and you can be slightly next to your vocal. So, this is sort of like assume you are listening from here. So you do know that vocal is just right in front of you and everything else just pan around that. Cool. We can take a look. This is very cool, actually. I think this is, traditionally when you are doing, this leveling and panning is usually just two sliders. So you basically just grab those, but this is sort of like turn that into a visualization. How you do it. So this is usually how you do it. So you have the level. So you want to see how loud this thing is, and you want to see whether I want to put it at the left and right. But Visual Mixer is sort of like doing these things for you. So, at the, y-axis is the loudness, the level, and x-axis is left and right. So this sort of like allow you to put it in that space. Of course, if you're a professional, you don't really need this. Let's look at these. Actually, I think we just need to listen to these.
Caught some feels, you keep your distance. I caught some feels, you keep your distance.
You hear that
Try to make
background
us
vocal
real.
further away?
I know I'm wishing, cause I'm stuck in the middle of something that I can't seem to change. In the middle of something.
Yeah, so basically you can grab these things around, and that actually just maps to these, level and panning. And there's actually something more. If these are stereo or, they can also do some algorithm to sort of make it wider, this, so you can see the shape. So you can, break a track into, wider or narrower, if those are stereo recordings. Cool. And also finally, reverberation. This is where it is. No, Vienna failed. This is the golden hall. So this is their main concert hall. So I guess the most famous, the most famous room acoustic that people want to mimic. So this is like a traditional, shoebox concert hall, and it has one of the iconic sound stage. But think about reverberation. It's about sound bouncing around. So if you're a listener sitting here for never been there, but if you do have the chance to be there, so of course you have this direct sounds that just like come in directly from the sound source, but there will be also other things coming in. So this is usually how we look at like the reverb. So, after some time, sound travel fast, but you still take some time to reach your ear. So, 100 millisecond, 200 millisecond, it reach you, depends on where you're sitting, but there will be also, other passes, path so that these sounds can reach you. So going from here, you could do, just like one bounce, three times, two times. So whatever, there's different ways. So these are called early reflections. So these are, think about, these are sounds that travel within controllable number of manageable, understandable numbers of bounce before they reach you. And of course, there will be lots of things because you think about these are basically sounds go from anywhere. So it's like a propagation of waves, and it will bounce back everywhere. So I'm just showing one of those. So some of these, things that arrive very late in the reflection, those are very chaotic because it's basically bounce to everywhere. So here I'm drawing these lines sort of like just assuming this is just a shoebox, but think about all these, decoration, all these things, it could bounce very randomly. So basically, you have the direct sound, of course. Early reflection sounds like just show delays, where you basically throw back and then you hear it. So in this room, this is studio light, and we have all these things. So you don't really hear a lot of reverb. Still, there's something, but if you go to some other room, concert hall, then you will hear that reverb. Late reflections, now irregularity appears, everything just blends together. It's much harder to model that. But that's sort of the idea of reverb. So what to do now? So the first thing is like, well, there are so many different audio effects. How do we even use neural network? It's like, how do you even think about this? So the first thing people actually try is called neural audio effects. So the idea is that, well, let's just take a step behind. Like, well, let's just don't think about, we would just do auto mixins magically at one shot. So now first thing is like, can we build a neural network that do a specific audio effects that we wanted to do? So think about where we grab delay. Well, doesn't sound too tricky. Delay is basically holding that thing and throw it back at a certain time. And think about reverb, then slightly more difficult than delay. Think about compressor. Think about EQ. Then how does these convolutional neural network might be able to do it? So this is basically the first thing people have tried to sort of like model audio effects as a neural net. So, look at this graph. You might feel like this is like a very tiny single, tiny neural network as something we've seen before. So basically here you have some control signal. Those are the parameters you want to do, say, reverb, how large, how you will have some knob, right? When you work with these, effects. So you grab an effect, say delay or say, EQ, and then you have certain parameters. You do know once you apply that effect, you do know what it sounds like. Now you want to train this model that take the original sound and the controls. Now you want to see whether you can mimic that output. Basically, that's the idea. So, we want to have the effects and we want to have the controls and the inputs to mimic that output. So, it's not too bad. We can listen to some of these. So one thing about this is actually, if you look at it, the effects doesn't actually take these controls. So the idea is that the model should be able to sort of learn to map that control automatically to the effects, the parameters. So this is what's something that we can do back in 2021.
Up in my head, oh, you're up in my head for good.
Cool. So this is the default reverb. So as we see here that, you train these kind of model with the default value of these things.
Up in my head, oh, you're up in my head for good.
And now you has all these different parameters and you can actually try to move around those parameters, see how those parameter works. And, they found out that -2, 1, you get the shorter reverb.
Up in my head, oh, you're up in my head for good.
And you have like longer.
Up in my head, oh, you're up in my head for good.
And this one is when they usually train these model, these inputs doesn't go very large, but when you try to push that limit, you will hear something interesting.
Up in my head, oh, you're up in my head for good.
And then for guitar, I think we won't play it, delay. That's the artifact. Amplifier, the guitar one. So this is the input. Oops. So the default is something like this. So these are actually not the input. This is just like when they play with these numbers, they realize these just sounds like this kind of effect. So it's not that intelligent as you might thought. It's just two knobs and you can play with it and then, oh, this just sounds like, soft, fast, slap. But anyway, it's something. Right? Or or if you hear it toward larger. So basically, you have things that's more controllable based on your, audio effects that you are using. That's in 0, 0. And now, the further away that you get, more distorted sounds, basically. So this is the first thing people try. Well, still 2021, so you can see how new this field is. But basically, that's one of the first thing people try in trying to use a neural network to mimic an audio effect. And now the interesting thing now becomes that, well, once we do know that neural network can become an effect, then how can you combine all of those to do something interesting? So this is called effects transfer. So basically the idea is that, well, think about how we apply effects in real life is that, well, you get some microphone inputs, you apply a bunch of audio effects, right? You won't just apply EQ, you will, also apply compress, apply reverb, apply a bunch of effects on all the way until you get the final outputs. So what they are trying to do here is that, well, we have the inputs and we do have some reference file that we do know well. This file is the automate, like reverb or the sound characteristic that I want to throw my input to. So now what we are trying to do is that go from this reference, can we sort of grab those parameters to predict what would be the reverse setup, what would be the EQ setup, what would be, anything like that. And now, even you have the input, you want to send it to the controller so that how do you go from your inputs all the way to your reference audio. So the reason why you do need this input is that, this input can potentially be a different instrument, can already be a different tone. So without the input information, it's much harder for this model to know, because this reference file could be going from any input file. You can get the point? Yeah, so you want to do differentiable, modification on top of it rather than just completely assuming that your input is completely dry. So you want to look at your inputs and like, well, it does have some certain amount of reverb. Now, how much we want to add to that? Or this is completely dry, then we just add that amount of reverb. So you want to see how far away from this input to that reference acoustic features, and how do you go from that to that. So this is how they do it. This is called self-supervised. So they didn't have to do, they didn't actually have to grab a bunch of data because they are doing this as, self-supervised. So you grab a bunch of, dry dry sounds, and then you do 2 sets of different DSP setup. So you see these knobs are kind of different. It's a little bit subtle, but you apply different effects on top of those. And now what you are going to do is that, now you have the first things with this effects and this one with the other effects. So now what you want to do is that, it's a bit tricky. So now you have the first song, the first part, and then you have the reference file, the first part of that reference file. Now you want to predict how to get those parameters. So your goal is to predict what those parameters will be. And now once you do know what that parameters will be, then you go from that parameter and try to sort of apply it to this XIB so that it throw it to the reference one. Well, this is a bit tricky to explain. But basically what you are trying to do is that, now you have these 2 things. So you want to do is that you want to grab XRA, the first part of that reference, and you want to apply it to your XI, and that XI will turn that into XIB. Not technical that. Not really. Oh, I explained incorrectly. So you have XI and you have XRB. You want to grab XRB's effect, apply it to XIA so that it throw XIA to XRA. Well, that's tough. I think I messed up similarly last year. So the idea is that, you grab, this is your input, the first part of this input, you have the reference, you take somewhere later in that reference file, you want to grab the information, the parameters from this reference file, apply it to XIA, then technically this XIA should sound similar to XRA.
Yeah, because the top one, well, the top one still like had some other effects, but like.
Yeah, so you want to redo it or you want to, it's not just redo it, you want to sort of, I mean, that's actually the big question.
Yeah, like I guess.
You want to go from this to this and then back to this, right? But in this case, it's like, can we just like, well, if there's more reverb, then can we do more reverb? It's kind of like that. But anyway, everything is neural. So technically, you don't actually need to worry about that because these neural effects could be doing reverb and de-reverb at the same time. But the idea is sort of like that. Cool. We can look at this video. That's very nice.
Second example, we can take a Bassy music recording and lighten it up. The Bassy input music sounds like this. The target style sounds like this. The input music again. And the stylized output. Here we see the low frequencies were
How do I get rid of these? This? Oh, okay.
cut, high frequencies were boosted, and compression was added to give it a more produced.
Yeah, so you see that, this is like the prediction, and you want it to map to that. And it will actually learn the EQ that highlight the high frequency part. As you can see here, the high frequency part are just gone in your, original unprocessed audio. Now you boost them to highlight the high frequency part. So, this is just the idea where, now because the things actually work because every single thing here are differentiable so that you can inference how you control these. So these are, DSP, these are real effects. But here, what you are doing here is differentiable audio effects. So you are actually learning differentiable audio effects that do that. It's differentiable 2 times. So this thing is differentiable, but it's also doing this differentiable effect transfer. So how do you go from this effects to this effects? That's what I call differentiable, or think about effects transfer. How can you transfer from this effect to the other effects? And that's being done with this neural proxy of your DSP. And it's technically not just your DSP, it's actually doing something more. Potentially, it could be, going back to the dry sounds and then apply the DSP, or, it just figured out some way, shortcuts, just do it. To do the reverb, or, EQ, the EQ, and then EQ back. Kind of. So that's the second thing. So, go from, can we model neural, audio effects as a neural net? Now, if everything can be differentiable, now we can do effects transfer. So now we can sort of like trying to approach this bigger issue of automatic mixing. How can we do that? So you think about what's mixing technically is doing is that, well, we have a bunch of different tracks and you want to do all sort of stuff on top of that file, right? So, the first thing you need to do is like, you do need to know what these songs are about, what these tracks are about, how loud they are originally, what's the, the recording condition. So of course you have to do something so that you do know what's going on in that waveform. So this is basically how this model is designed, where you get n different waveform, like each different track, like drums, guitar, bass, piano, and you do want to go through some encoder, and this encoder is actually already pre-trained. So these models are built to already know something about the audio, and everything will add together as the context. So, one thing about auto mixing is about, how do you know the other tracks, how loud they are, and how do you do the balance? So you add everything together, and then now you send it to this post processor. So this post processes is basically trying to, get two things. So once it's like I have this track, I know what's the features of this track, and I also know what's the mean embedding. So what's the overall setup is like. So you do know what other tracks sounds like, kind of. So this post processes basically just predict based on these two things and try to predict those parameters. And these parameters, think about it just like the neural audio effects that we talk about. These parameters will be sent to these neural effects so that being applied on top of these waveform. So now you have these transformation network. Now you grab this waveform, and this is just a shortcut here. So you send these things and plus that parameters, and you get the mixing result. And that's how you get it. So this transformation network is just a bunch of stuff, but basically this is trying to mimic how people do neural, mixing. So this is the transformation thing. And basically what it does is this. So you will do gain, it will do polarity inversion. So think about left and right, it could be swap. So this is handling where that it's LRR or it's the opposite way. You will apply several EQ, compressor, reverb. All of these three things are being modeled as a neural audio effects, the thing we just look at. So that's these three things it's about. TCN, I don't really know what T is. I guess it's a transposed convolutional neural network, but I'm not quite sure what T stands for. But after that, fader and pan. So, these things doesn't need to be neural because those are just simple stuff, right? Gain is just, just changing the dynamics, changing the loudness, pan is just like moving around the L and R. So these doesn't have to be neural. But these three things is a bit complex, so let's see, can we do it neurally? So now, basically now you get a differentiable mixing console so that you can train. So, if you look at this, everything is differentiable. So go from the waveform, you extract some features about that waveform. You do know how loud it is, what is the sound acoustic, what is, what is that instrument basically. And then, together with those information, but the context information, you predict how you should mix that. And then, with that parameter, with the waveform, now you go through this, processing, and you get the process track for that, and apply it to all the tracks. Now you get the mixing output. And so, basically now you can train it. So you get a bunch of like dry waveform into it. And then you have the output mixer, mixing outputs, and then you just train these kind of model. So this is like just, doable because everything is differentiable and trainable. So this is like a differentiable mixing console, if you can think about it like that. So what we can do now is that, first, let's look at this transformation network. So the things, so one single track, can we make mix? So this is just testing this transformation network. So if we have the same. Actually, it's not just one single track. And so if this is our target, oops. And we can actually map it to our outputs. So this sounds more like a raw mix. Yeah. Cool. So you can do most of the things, the more further away. And what you can get. You could also do all sort of different things, drum mixing. So in this case, it's all the same mixing style. So if you just directly mix all this drum sounds together, usually that's not what people do. So usually you have like microphone on each of the drum kits, hi-hats, cymbals, and there will be overhead, and kick drum, you will also have a microphone. And if you just mix them together. That's what it sounds like. But this is what you want to get as a target. So this is what you can get. Oh, this is not direct mixing console. This is the differential. This is what we get. Sorry about that. So what we want is this. It's not separate. So you have all these mono track for your drum. So every single drum you have a. So this is what you get. I put it in the wrong order. This is what you get if you don't do anything. You just grab them and just play them together. This is what you get. So it's like you have all the drums at the same place and you keep it everywhere. So you have bass drum, snare drum, hi-hat, all at the same place. So there's no space. And now this is what the differentiable mixing console can do. Yeah, so if you look at the drum set, like hi-hat is at your right, and bass drum in center, but toms will be at the right, and right at the left, and cymbal at the left. So you do know there is some spatial going on there, and this is what you get. This is the real mixing up. So you can likely see we are still far away from that, but at least it's better than that you mix it up. And you can also do that for multi-track. So if you just mix everything mono without any processing.
Ici, sous les rameaux flottants, je les suivais dans leur gaieté si tendre. Ils échangeaient des mots pleins de douceur. C'était mon frère et puis ma sœur.
So this is what the model can do.
Ici, sous les rameaux flottants, je les suivais dans leur gaieté si tendre.
So you can hear the reverb, but also leveling, so that the vocal is not too dominant. But this is like a human mixed output.
Ici, sous les rameaux flottants, je les suivais dans leur gaieté si tendre.
This is much better, of course. Yeah, so you see the leveling and reverb, but also panning a little bit. But also this is another example where like the raw mix.
Well, I woke up this morning.
Everything in the
Down my door.
same place.
I could tell my milk cow, I could tell by the way she lows. If you see.
And this is what the model can do.
Well, I woke up this morning, looked down my door. I could tell my milk cow, I could tell by the way she lows. If you see my milk cow.
So nice to listen to these at this.
Well, I woke up this morning, looked down my door. I could tell my milk cow, I could tell by the way she lows. If you see my milk cow, please.
And I guess this also suggests that there's something going on with mixing. There's some, it's like you don't recognize that something is mixed in, not the way it should be. So you do know that, partly because, there's a general trends how people mix audio or for specific genre. But at the same time, it's like, there's some, rules that people are more familiar with about this mixing outputs. So that's also part of the reason that, why auto mixing can be done kind of. And of course, at the end, there's a lot of like artistic decision in how you do the mixing. So, whenever you think about mixing, it's not just like finding the correct answer. It's also, partly about, that's also part of the music creation process. It's like mixing can also influence a lot how you place these different sounds. And if you're the producer, you also have to think about, from the mixing perspective, it's like, well, now you're recording all these sounds in mono, but without that understanding of what's the final placement you want to do it, how do you want to mix it, and how do you even know what you are aiming for when you are recording these sounds. So it's all integrated together, and of course these AI models doesn't know your intention, right? So but at least these automatic mixing can be as a good starting point. And as we see in the music creation part, where it's always so simple to just generate something without any controls. And now people are looking into this automatic mixing. This is like ongoing, and people are thinking about these audio effects. It's like, well, do we really need these knobs? I mean, we already have these audio effects, and do we really need this automatic mixing? I mean, what we are aiming for could be, can we make something brighter? Can we make that sound more prominent? Can we expand the sound stage? These sort of more meaningful or more intuitive, natural ways to interact with this interface. And so I guess that's also why nowadays this agentic AI thing is going on, is where, you have this ChatGPT that does understand what you are trying to instruct the model to do. But now how do we go from this to something that actually understand human intention? And I guess there's still a huge gaps, and this like 2021st, but I don't know when we will get something like that, but there's still tons of things to be done in this field. If you're interested, there's actually a nice tutorial. So Christian Steinmetz is sort of one of the leader, pioneer in this field, deep learning for automatic mixing. There's tons of gold in this tutorial. So I want to switch a little bit to something even broader than thinking about where you are basically chaining these audio effects. But there's also another paradigm of music creation, if you know Max MSV. So another have you tried Max MSV? Okay. I'm teaching in another class. It's fun. It's totally a different idea of doing music. It's more like signal processing. So think about in W you have lab view or you have these waveform generator, and then you send it to something. But think about it, at the end you want to send it to speakers, and then you get those waveform out. So you have sine wave, you have another sine wave, and you have another sine wave. Try to add them together, or do some filter, do some delay, do some audio effects, distortion, and then you get the outputs. So this is sort of like thinking about audio processing graph that there's tons of different ways. So you have inputs, you can do all sort of like different things, bandpass filter, I don't know what LS is, but this is likely ping pong effect or something like that. Yeah. So, just sort of like, think about Max MSP or things like that. Can you generate these things? So this is essentially what they're trying to do here, estimating audio processing graph. Can we generate these graphs? Basically, that's the idea. So this is like beyond that, traditional way of thinking about, music editing or audio effects that, apply EQ and then compressors and reverb, and well, add them together. Voila. So this is, think about another way now. There could be different audio processing graph. So there's tons of processors. So low order linear filters, low band, low pass, band pass, high pass, band reject, different order of that. Equalizer, crossover, phaser, but there's also chorus, flanger, vibrato, ping pong delay, reverb. There's also distortion, beat crush, blah blah blah, pitch shift, mix panning, mid-side splitter, mid-side merger. So basically, if you have a stereo inputs, you can separate them into side channel more versus middle channel, or you want to put it into more mono-like. So mono versus stereo thing. And you also have, oscillator. But anyway, these are the data set. There are like 3 data sets, so they are sort of like distinct. But at the same time, you sort of like cover different kinds of audio processing graph. So the idea, we don't have time, but I guess the idea is that, well, once again, we can actually tokenize this graph. So what does tokenize mean? So now it actually started from the very end. So you have the first output NOT, so V1, that's the first one. And now you have the V2, and then you have the edge, and then you have V3, and then you have the edge, and then V4, and you have the edge. So these are basically how you do it. So token type is like whether it's a vertex or it's an edge. And then node ID will be these numbers. And the node and edge type is basically what essentially these things are. So in this case, out, ls, the delay, and this is basically your input. So this is basically like you can use a transformer to generate those, because now you can tokenize it. So all the way from the outputs, can you generate these processing graph all the way until you reach the input. So that's essentially what they want to do here. They are actually doing blind estimation, where that means that you don't really know what the input is. You just try to guess how do you even get the sound. So that's what they call blind estimation framework, where source are not given. But the idea is that, well, we basically just want to use a transformer to get those. So, you started from, some inputs to get started with, and then you want to generate all these things by transformer. And so this is called tokenized graph transformer. And once you do what this shape is like, you still don't know what that parameters will be, right? If you have like low pass filter, you have delay, you do want to know what the parameter for those is. So the first thing they do is that first you generate the graph, but you don't know the parameters. Now, given this graph, now you predict the parameters. So that's the 2-stage things they do to enable this, and you can actually get something like that. We can just listen to it and call it a day. So this is what you want to go. So this is the estimation. So technically, they are doing blind estimation again, where you only know about this. And that's all you need. And the model will just learn how to go from this to this. Oops. The reverb is too large for the kick, but you get the sense that basically is that looking at, listen to this sound, and you try to guess this effect computation graph, and now you apply this to the unknown dry inputs, and that's what you get. So you can see that, well, it is fine, but at least now we sort of like going beyond that fixed processing graph. So if you think about the traditional way how previously this differentiable things is doing is that, well, we always apply EQ, but you can do it without EQ, right? You can set every parameter to doing nothing, or compressor doing nothing, reverb doing nothing, but still you have that fixed processing graph. And now here we are thinking about, well, potentially I don't need to apply effects on all the channels. It could potentially only apply to a certain channels. And even more interesting, in Maxent SP is now, if you have feedback loops, if you have more complex structure, of course, here, if you want to do tokenizing, it's much easier if everything is sort of like, that's like a cyclic without loops. If it's a graph without loops, it's much easier to tokenize it. Cool. We are getting to the end of the course. Yeah, almost done. But editing, music production, this is very, 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 very recent. 22. And there's a lot of things going on, especially on DAW manufacturers. Yeah. So a lot of exciting things is going on in this field. Cool.